Now regarding the thermodynamic and basis, it is just the basis of the thermodynamic. The thermodynamic basis first, the first law of thermodynamic, which is delta U equal Q or delta Q plus delta work. Some textbook or the majority of textbook write it with minus, and some textbooks writing it with plus. Yet it is all rely on the definition of the work itself. So if we are keeping it in this form, which is with plus, that is mean whatever enter to the system is with plus. So if heat, it will be plus. And if I made a work on the system, it will be plus. So we're using this form. Okay. If I'm going to use minus, so if the heat going to the system, it is plus, and if the work done by the system is plus, so minus is correct. Of course, if the sigma for an entire cycle, like a piston going up and down or refrigeration cycle, if the sigma work with positive, that is mean the cycle is a power generative cycle, like the motor. And if it is the sigma of the work is minus, it is a heat cycle, which is like refrigeration. We are doing work to transfer the heat. Okay. So if it is negative, of course, if we're using this method, which is work out and in. Okay. So this is general. This is just the general. Delta U is the change in the internal energy. Okay. So the change in the internal energy in a system, or in a closed system, is the change of the heat in and out and the change of the work in and out. Okay. Also, we have some ideal gas relationships, which is the famous BV equal MRT, and gamma, which is some are saying it kappa, etc. Whatever is gamma, which is CB over CV, and R is the constant of the gas, which is CB minus CV. Okay, delta U is CV delta T. Of course, this one bare unit mass. Delta H, since Halby, is CB delta T, which is bare unit mass. This ideal gas, ideal gas. Okay, and also we know that is T ds. ds is the change of the entropy. Okay, equal du b dv, and also dh is equal du b dv v db. Okay, if we apply the same concept here to define the entropy relationship, why we are going to check this schedule. So the entropy relationship, which is dt, so ds t down down, so it will be du by t plus b dv by t. Make an integration. It is s equal cv ln, because it's t and it is 1 over t, the integration of 1 over t. It is ln t2 over t1, because it is, you make the integration from t1 to t2. Okay. How you put like this? You put it like this. That is du equal cv dt. Okay. So it's the same also concept. You're going to do it. Okay. Okay. And so it will be s equals cv ln t2 over t1 plus r ln v2 over v1. And also, if we're using the same relationship, but we use this relationship, so it is ds equal dh over t minus vdb over t. So also s, which is entropy, equal cb ln the ratio of the temperature plus the r ln ratios over the volumes. Okay. Now, Are we going to use such? Yes, you can use it. Okay, if the Cb and Cv, I don't want to use the ideal gas, so Cb and Cv is not a constant. So we're using something named stagnation. Stagnation is the entropy at the stagnation, which is ds stagnation. You can find it in all thermodynamic tables for the air, etc. So ds equal ds stagnation plus r v2 over v1, or ln, or ds stagnation minus r ln b2 over b1. Okay, stagnation we can get it for point 1 and for point 2 minus point 1 and point 2, you will get delta ds stagnation. You have volume 1 volume 2, put and r cv minus cv, and it is constant. This is changing, but this is always constant. Okay, so you can get the entropy, the ds entropy. This is how the way we're going to use it. Okay, but we need to know what is the cycles we have in thermodynamic. Thermodynamic is very easy. We have some famous cycles, which is our thermal process, which is isothermal, dt equals 0. So when dt equals 0, as we discussed here, from this equation, so, and based on bv equal mrt, and dt is equal 0, so bv is constant. Why? Because the temperature here is constant, isothermal, no change in the temperature. So BV should equal constant. This constant, 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 so it is equal constant. So BV equal constant. In the same while, if BV equal constant, so there's no change in the internal energy. If there's no change in the internal energy, which is mean Q plus work equal 0. Okay? And the work is B dV, which is mRT ln V2, V1 over V2. Okay. Isochoric. Isochoric when the constant volume same, so B over T equal constant. No change in the volume, which is means the work is 0, because work is B dV. Okay. So change in internal energy is equal to the heat, and we know that the internal energy is m dot or mcv dt. So Q equal mcv dt. Okay. Regarding isobaric. Isobaric when the pressure is constant, so same concept, V over T equal constant, which is mean du, first law of thermodynamic, equal dq plus dw, or del w, del q by del w. And based on this, see here, because it is isobaric, no change in the pressure, we know that is the Q is mCb dt, which is the change in the enthalpy, and the work is B dV. B dV. Like this, we can get the total change in the internal energy. Okay. Isentropic. Isentropic, which is mean, which we already discussed here, no change in the entropy, which is mean this equation is equal 0, or this equation is equal 0. When this equation is equal 0, ds is equal 0, which is mean, just to rotate it back again, if this one is equal 0, or this one is equal 0, you will find yourself is this term is equal minus this term. Okay? No change in the entropy. Put it here, you will find left term and right term the same. So based on this, BV power to gamma equal constant, or T power to gamma minus 1 equal constant, or B power to 1 minus gamma multiplied by T over gamma equal constant. And also there is some consideration, which is BRs. BRs, it is a certain, it's not a pressure ratio, but it is BR value, which is pressure, which is indicating for the isotropic process. Okay, so the BRs in the table, for example, at point 1 and point 2 at the temperature ratio is equal to the normal pressure ratio, okay, which is the rest pressure. Okay, this from thermodynamic tables we can use it. Of course, based on this, isotropic mean by its definition no change also in the heat, which is mean adiabatic. So the adiabatic process is not change in the heat. So isotropic process, it is reversible and adiabatic, so it will be isotropic. Okay, which is dq equals 0, and from this, so work is equal mcv delta t, or like this. Okay. Polyopic, it is same like this one, same, but without going as a reversible. No, there is a change. It means it's not reversible. Okay, so it is not reversible. Now, so with a condition in, which is gamma for air is 1.4, between 1 and 1.4, BV power to n equal constant, just remove the gamma, keep the n, but based on this, Q is not equal 0. So Q is not equal 0. There is a loss of energy. There is a loss of heat. So that's why it is not reversible. If there is no loss of the heat, it is reversible. But now it is not. There is some loss. So this is the first law of thermodynamic. Same. So Q equal M R delta T 1 over gamma minus 1 minus 1 over N minus 1. There is a big derivation about it. You can read it from the text box. Also, the work is always the same, BdV, and etc. You can continue with the same. This is in general for the thermodynamic and heat principle. So also another principle in the thermodynamic is the cycles. Before entering the cycle, I need to define this one and this one. To define this one regarding the mixture, if you have any mixture in thermodynamic, which is mean by mixture, gas and the vapor and the liquid of the same gas, okay, like in water, steam, in anything which is has a mixtures, okay, any properties, not only S, but let's say entropy, is equal to the fluid, the subcooled fluid entropy plus the fraction of the mixture multiplied by the change in the entropy from the subcooled to the superheat, which is mean from the fluid to the gas. From the table you can get it. Or it is X multiplied the same. You can change S, you can write whatever you want. Pressure, temperature, whatever. Okay? And but of course you need to use the SFG or whatever is whatever FG, okay, from the table. And X is how much gas over how much total gas plus fluid. The other one, when we are going to use the ideal gas with the equation CV, CB, etc., the table before, we need to understand that the gas should be, its temperature should be higher than 300 Kelvin, and pressure should not cross from 10 to 15 bar. If it is crossing from 10 to 15 bar, crossing, which means less. Yani if it is 20 bar, no, you cannot use the equations. You need to use the tables only. And if the temperature is less than 300, especially if it is less than 200, especially, you cannot use it. You need to use tables. However, you can use the tables anytime. Why? Or it is more accurate, but it is time consuming. Now we're going to go to the refrigeration, also not refrigeration, the thermodynamic cycles. Thermodynamic cycle is, I will go just quick on it, but it is cycles. For example, the refrigeration cycle. Refrigeration cycle, we're going to discuss it later. It is heat out, work, heat in, condenser, then return back, expansion valve, and this is the compressor. This is pH curve. Regarding TS curve, in TS is the same. It is, we assume it is isentropic in the compressor. Then go for heat loss. This is temperature. When it is coming in the mixture, temperature is constant. Then it is go like this, then like this. Okay. An assumption. It is an assumption. When you open, it will be in the refrigeration better, but in an assumption with a constant enthalpy, almost the entropy for refrigerant or the steam is constant, almost. For example, I'm going to open. It is from the thermodynamic graphs, which is, you can check it. I think so. This one's, yeah. For example, I will take example for here. I don't know what is this even. It's like ammonia. You see here, this line is the entropy. The entropy almost constant with constant enthalpy. Okay, so with constant enthalpy, it is almost constant in the subcool, of course, not in the superheated, not here also. Another graph. For example, by the way, this is constant pressure, and this is enthalpy with steam. However, we'll return back in detail later, okay? And this is a PV, okay? Refrigeration, it is a heat engine, which is its efficiency if you are using it very straightforward, assuming that is ideal gas, etc. It is, this is for the Carnot cycle, okay? I'm speaking now about Carnot cycle with the heat engine. It is 1 minus TL over TH, and the COP of refrigerant TH over TL minus 1, and the COP for heat pump is 1 minus TH. Refrigeration is a type of Carnot cycle. Okay, Carnot cycle is the same. It is compression, heat out, isothermal expansion valve, or in expansion, or in the piston, or whatever, then adiabatic, again heat in. Okay. Okay. And this is TS curve, of course, always in increasing of entropy, the cycle will go. So if it is go from here to here, it will increase the entropy. It will go from here to here, increasing the entropy. Okay. Now it is Otto cycle. Otto cycle, it is not like heat engine, but it is now, if you compare it with this one, if you can see here, is it changing, which you can check it here in Otto, is isentropic, then not isothermal, it is isochoric, then, which is no change in the volume, then no change in the entropies, and no change in the volume. This is Otto cycle. Okay, this is case CV is equal constant. You can use this as efficiencies. Ericsson cycle, you can even check it from here, which is, it can be applied for same concept. For electron cycle, it is isothermal, then isobaric, then isothermal, then isobaric, and this is a TS. Okay, and this is isobaric. Of course, you can go to Brayton cycle, even Brayton cycle like the turbines, compressor and turbine cycle, which is the gas turbine like example, which is isotropic, then isobaric, then isotropic, then isobaric, which is isentropic, adiabatic, then isentropic, then adiabatic, which is here heat out, turbine, heat in, compression, which is rotate like this. Okay. Diesel engine, you can follow the same. Stirling cycle, same. Rankine cycle, the same. This is the last one, which is where it is just the steam cycle, which is with even the overheat, the reheat, etc. It is the same concept. This is regarding the combustion ratio and the cutoff ratio, which is some equation for the diesel cycle. The combustion ratio is R, which is volume 1 over volume 2. A usually is equal 18. Cutoff ratio, which is volume 3 divided by volume 2, usually is equal 2. Stage 1 is usually it is at 100 Pascal, kilopascal, and which is the normal temperature pressure. And you can see here the combustion ratio and cutoff ratio. 1, 2, 3 is the same numbers here.